Hello, everybody. Welcome to this very brief introduction to polar coordinates, and then we'll talk a little bit more in class. So far, all the time we've been using Cartesian coordinates, and there to represent points, we have to know how far we have to go along and how far we have to go up. So those are our two coordinates. Instead, sometimes representing curves and other things, it can be more useful to use polar coordinates. And then we also use two numbers to represent points, but they have very different meaning. We represent points by knowing how far we have to travel and what direction. So rather than knowing how far across, how far up, we might want to instead use how far we have to travel and what the direction is. So let's get started. Okay, and as we talked about with Cartesian coordinates, the steps are normally we fix a point, which is our origin, which is called, we typically call 0. And then points are represented by x comma y, where x is the horizontal distance of the point from the origin and y is the vertical distance of the point from the origin. Instead, with polar coordinates, we make the same beginning. So we fix a point, which is sometimes called an origin, sometimes called a pole in polar coordinates, but it's the same thing. And then we fix a polar axis, which is just a positive half line starting at the origin. This is our kind of 0 direction. And typically this is represented as the positive x-axis. And then points are represented by a pair r comma theta, where, as we said, r is the distance of the point from the origin, so meaning the hypotenuse, not just the along or the vertical, but the actual distance. And theta is the direction or the angle between the polar axis and the point that we have to travel. So here positive angles are supposed to be counterclockwise. So here is the idea on a picture. We have some point which is at the end of this diagonal line. It's r comma theta. What does that mean? Okay, it means that the distance from the origin to the point, so from O to P, is equal to r. And the angle that this point makes with the polar axis is equal to theta. And if the angle is positive, then we'll be traveling counterclockwise. Okay, and it turns out every point we can represent in this form, r comma theta. But the r and the theta will, of course, be very different to the x and the y that we're used to in Cartesian coordinates. Okay, so this all makes kind of sense if r is positive at least, and it makes complete sense. There are also some extra little special cases if r is 0 or if r is negative. If r is 0, then we just have the point be the distance from the origin is 0. So the point will always be at the origin regardless of what direction we travel, which makes sense, right? If we move a distance 0 and we travel in any direction, well, we're still going to move to distance 0. We're still going to be where we started. So if r is 0, we are always at the origin, whatever theta is. And if r is negative, we make a convention that, okay, it doesn't make sense to travel a negative distance, but we make the convention that it's the same point, but on the opposite side of the polar axis. So rather than being here on the top right in the picture, if I was negative, it would be in the top left. We just flip the point in the pole. Okay, so as we just said, if r is 0, 0 comma theta represents the pole O for any theta. And if r is negative, we just flip the point through the pole. Okay, and with this, negative r comma theta, which is flipping through the pole, is the same thing as r comma theta plus pi. So theta plus pi would mean we take our regular point and then we rotate all the way around, and we would still get the opposite point on the other side. So rotating through 180 degrees and flipping through the pole is the same thing. This is the same thing. Okay, one thing to keep in mind in polar coordinates is that there are different ways to represent the same point. So it's not like x comma y where every point is represented once and only once. For example, all these points represent the point with Euclidean coordinates 1, 0, but these all have different polar coordinates. For instance, we could travel a distance 1 make an angle 0 with the positive x-axis. That would get us to Euclidean coordinates 1, 0. Or we could travel a distance 1 and we could move through an angle 2 pi. Okay, 2 pi is the same, obviously, as 0 for the purposes of directions. Or we could move a distance, we could move at an angle pi, which would take us to the left. But then we can move a distance -1, and we said with negative r, we flip. So we will be moving over to the left, and then we flip. We will get back over to 1, 0. And then the same thing with -1, 3 pi as before. Okay, so there are different ways to represent the same point in polar coordinates. It's an unfortunate fact of life. Okay, so how do we convert between Cartesian and polar coordinates? That's one thing we might want to do, right? We're pretty comfortable with Cartesian coordinates. So if we want to answer a problem in polar coordinates, at least one way is to move back to Cartesian coordinates. Okay, we don't always want to do that. So how do we convert? Here is the picture, right? We have a point P, we have our origin, we have the polar axis, which is our positive x-axis, and we have all the different quantities on the picture, right? We have r, which is our distance, theta, which is our angle in polar coordinates, and then we have x, which is the horizontal distance, and y, which is the vertical distance in Cartesian coordinates. And if we want to translate from one to the other, we can use simple trigonometry. Right, if we want to resolve r in the horizontal direction, r cosine theta is going to give us the x. If we resolve that in the vertical direction, r sine theta is going to give us the y. And then if we want to go backwards, well, x squared plus y squared will be equal to r squared cosine squared plus r squared sine squared. We pull out the r squared, we get r squared cosine squared plus sine squared. Okay, x squared plus y squared equals r squared. And then if we do y divided by x is going to be r sine divided by r cosine. The r's are going to cancel. We end up with sine divided by cosine, which is tangent of theta. So depending on whether we're going from polar to Cartesian in the first equation or from Cartesian to polar in the second equation, we can convert either way. There is one thing to keep in mind though with the tangent theta equals y divided by x. This doesn't give us all the information. For instance, if we start with the Cartesian point 1, 1 or the Cartesian point -1, -1, the points are different. They're going to have different coordinates in polar coordinates. But 1, 1 and -1, -1, if we do y divided by x, we're going to get 1 in either case. So we want to be a little bit careful. For instance, the point 1, -1, which will be in the bottom right quadrant, it has tangent theta equals -1, but there are different values of theta that satisfy -1. For instance, 3 pi over 4 and 7 pi over 4. But 3 pi over 4 would be in the top left quadrant, whereas here we are supposed to have a point in the bottom right quadrant. So we cannot choose the first value that comes to mind, which is 3 pi over 4. We want to choose 7 pi over 4. So we just have to be a little bit careful when we are converting from Cartesian to polar. Sometimes there are multiple solutions of tangent theta equals y divided by x, so we have to make sure we choose the value of theta in the right quadrant. So top right, top left, bottom right. Okay, next up is polar curves. So we're used to plotting curves in Cartesian coordinates. Either we have y in terms of x or x in terms of y, or there is some kind of equation. And the points on the curve are just all the points that satisfy the equation. So it's similar with polar coordinates. Maybe we have a curve represented r in terms of theta, or we have some kind of equation involving r and theta. So the point in the curve is the collection of all points in polar coordinates that satisfy the equation. And since the same point can have multiple polar representations, we have to be a little bit careful. So we mean all points that have at least one representation in polar coordinates, which satisfy the equation. So to sketch curves, much like with Cartesian curves, we can either plot points, so we can make a r comma theta, we can plot some points and then join them with a curve, or we can just kind of use reasoning. So if r is something, that means the distance is something. What does that mean? If theta is something, what does that mean? As we'll see in a second. Or we could try to convert to a Cartesian equation using the conversion that we just talked about. So we'll see more examples of this in class. But here are some very simple curves, and they also kind of motivate why polar coordinates can be useful, because we have curves that are a little bit more complicated in Cartesian coordinates that turn out to be very simple in polar coordinates. So here, for instance, the curve r equals a, it's the set of all points r comma theta in polar coordinates, where r equals a. Okay, what does that mean? R equals a means that the distance of the point from the origin is equal to a. So we're looking at all points whose distance to the origin equals a. Okay, clearly that's, by definition, it's a circle of radius a. So circles with center to the origin are very easy to represent in polar coordinates. Okay, and then if we think about theta equals a, what does that mean? It means all points which make a direction equal to a with the positive x-axis. Okay, and it's a little confusing why I have both sides, but remember, clearly the top right here is on the line, but the points on the bottom left are negative r. So here I have a negative r, but still with angle a. We get flipped over through the pole, and we get also the bottom left. Okay, so we'll see many more examples in class, but I didn't want to do too many more complicated examples here. Okay, a little bit about symmetry. Just like we have symmetry with curves y in terms of x or x in terms of y, we have the same kind of thing in polar coordinates. So if the polar equation connecting r and theta that defines the curve is unchanged when we replace theta by negative theta, okay, that has the effect of flipping through the polar axis. So that means the curve is symmetric about the polar axis, right? Theta and negative theta are on opposite sides of the positive x-axis. If the equation is unchanged when r is replaced by negative r or theta by theta plus pi, okay, that has the effect of flipping through the origin. So this curve will be symmetric with respect to 180-degree rotation around the origin. And finally, if the polar curve is unchanged when theta is replaced by pi minus theta, then the curve is symmetric about theta equals pi over 2. But these are the main two. If it's symmetric when theta is replaced by negative theta, or if it's symmetric when r is replaced by negative r, then we have some symmetry. Okay, to wrap up this section, one thing we need to be able to do is to find the equations of top tangent lines, at least in Cartesian coordinates, for polar curves. So if we have a polar curve, r in terms of theta, we want to find a point on the line, okay, that we can do using the conversion equations we talked about. But if we also want to know the slope of the line, that means we have to find dy dx, right? We're finding the equation of a tangent line to a curve. As always, we want to find dy dx. So if we're starting with r equals f of theta, one thing we can do is we know that x equals r cosine and y equals r sine. If we plug in that r is f of theta, that means we can get an equation for x just involving theta. We have x equals r cosine becomes f of theta cosine theta. And similarly with y is r sine theta, we replace y by whatever it is in terms of theta. Now we have y equals f of theta sine theta. And if we forget where that came from, now we have an equation for x in terms of theta and y in terms of theta. Okay, now we have a parametric curve. So we could just use all the tools we already had for parametric curves to find the equation of the tangent line, right? dy dx is dy d theta divided by dx d theta. Okay, so we'll see that some examples and some more complicated curves in class. Thanks everyone, see you next time.